Okay, so hope this is audible to all of you, right? Is this
Yes, sir.
okay? So now we are going to start the session of today. Uh, so uh, okay, so okay, so we have started last time about the convolution. I think this screen is visible to you, and my voice is completely audible. Then we have discussed about the convolution operation in last lecture and a few examples that we have already solved. So convolution operation can be applied between the system response h of t and input x of t, and then finally y of t, output y of t can be produced. So here we can see that convolution operation can be applied only for the system which is linear time invariant LTI system, and the convolution operation is applied between the input x of t and h of t, and this can be represented by the symbol star. And then after applying this convolution operation between this x of t and h of t, here one can get the output y of t. So this part we have discussed, and we have discussed about the discrete time convolution where the input signal x of n is a discrete time and the system response h of n is also a discrete time. Then the output y of n is also obtained as a discrete time signal. So the equations which can be used for that one to represent the convolution operation is, if there is a x of k is the input, h of k is the system response, and y of n is the output, then y of n is obtained as a convolution operation between x of k and h of k. So this operation is the convolution operation, and this can be briefly described as the addition of all this overlapping point 1 to n. 1 to n means this all the points are overlapping points. We have to add this overlapping function between x of k and signal h of n minus k, and then we can produce a y of n. So h of k is undergoes through the three operations. The the two operations. The first operation is we need to produce h of minus k. So right, h of minus k. So that is the folding operations can be applied on h of k. Then the second operation is the shifting operation. Apply is h of n minus k. Then we can multiply the signal x of k and h of n minus k. And for all the points which are overlapping, overlapping means where x of k is present and h of n minus k is present. So all these points are added together to produce a y of n. So this part we have discussed, and we have taken into example one example where x of k is given at t is equal to 0. K is equal to 0 and k is equal to 1. The two values are obtained 1 and 2, and this is x of k can be represented by the amplitude over here. H of k is represented with the two values of 0.5 obtained at k is equal to 0, and k is equal to 1, we can obtain 1. So that h of k is equal to the value of 0.5 and 1, that we have x of k and h of k. So we apply this operation x of k into h of n minus k to produce the y of n. So after doing this operation, we have studied the two methods basically. One is the graphical way to find the convolution operation. So in this way, we can fold the h of k to h of minus k, and shifting is applied with the n. The variable is n, which is the variable for a shifting. How much shifting is applied depends on the value of n. So if n is equal to 0 means no shifting is applied, n is equal to 1 means 1 point shifting is applied, and if we move n further and further, so more and more shifting of h of minus k is applied. So for every times, every shifting, we will multiply all the, or we will multiply, we will find the overlapping area, and overlapping area is the area in which all points of overlappings are to be considered. X of k is multiplied with h of n minus k, point to point, and for all such kind of a overlapping point, we need to identify, and then we have to add up. So then we can start with n is equal to 0, then find x of k and h of minus k assigned to y of 0. Then for n is equal to 1, we can assign as a y of 1. N is equal to 2, we assign as a y of 2, and so for all these points we have identified, and then we assign to the y of n, right? So this part we have covered. We have taken one example of this, and we have even discussed for every LTI system this part is already discussed, and we have even taken one more example in which rather than graphical method, there is another method which is even equally powerful method, and that is known as a graphical tabular method. In a tabular method in which we can arrange the x of k in ascending in order from starting from k is equal to 0, 1 and 2. In a vertical column, we will arrange h of k from starting the value of k is equal to 0, 1 and 2. These are the amplitude values at the point of 0, 1 and 2 respectively, and the same way these are the value of x of k. This all 1 are the amplitude values of x of k at k is equal to 0, 1 and 2 respectively. Then we arrange them, we multiply all this row value with this column value, and we put in the particular slot. Then this one is multiplied with this one, and then we obtain this one. This one is multiplied with this one, and then we obtain here this one, and so forth. We arrange in this order. After this, we make the grouping. We draw or sketch the cross line over this, all with joining all these points. And when there is a group, we add this all the group one by one. First we add this one, then it's only the value of 1. Then we can have this one, then we have this one, we have this one, and we have this one. So we add all these values, and then finally we put here. But now once you have y of n is obtained by this tabular method, we don't have idea about where the t is equal to 0, which is the reference line, right? Where the t is equal to 0, or this amplitude is located at which value of a time axis, we don't know. The same way, if we know about one, we can locate this first elements of y of n at the particular time axis value, then all others we can identify easily, because the next value will be located at, if this value is located at some t is equal to 0, next value will be located t is equal to 1, next value will be located at t is equal to 2, and so on. So at least we should have idea about the first point. So for that one, we can use this this axis. This axis is known as a t minimum axis, in which it is x axis of y of n, right? And these are the amplitude values. So first we need to find at which t equal to 0. So we have a formula. T minimum, this point is located at actually the T minimum point, and this point is located at actually T maximum point, right? So all other points are located between this T minimum to T maximum point. So T minimum point can be identified as the minimum value of T1. So T1 is actually the axis of x, T2 is the axis of h. So we'll find the minimum point of T1 means minimum point of the time axis of signal x, plus minimum of T2 means minimum point of the time axis of signal h of t. Then we add both together, and whatever the answer, that will is the minimum value of our time axis of the signal y of n, right? So that is the minimum point of time axis for the signal y of t. So that is 0. It means the first value here 1 is located at the value of t is equal to 0. It is not necessary always we have a t is equal to 0, but whatever the answers that we obtain by these equations that we follow. Now once it is identified, the other can be identified easily, because then the next would be a t is equal to 1, then it is equal to t is equal to 2, then next to next would be t is equal to 3, and so proceedingly all the values are, so one value added with the previous value. But Still, if you want to identify this T maximum, so we have to find the T maximum by using this formula. Length of T1 means the number of element in a time axis of x of t signal, plus the length of T2 means the number of points in a time axis of signal h of t. So it is the length of it is the length of x of t signal, and this is the length of h of t signal. We add both the lengths, and then we find the variable L, which is the addition of a length of T1 plus length of T2. So we are obtaining here the 6, and then the T maximum can be identified as by this equation T minimum, which we have already identified here, plus whatever the variable L we can find from here, L minus 2 will give us the T maximum. So in this case it is 5. So it means the T maximum point at which the last value is located of signal y of n, it is the T max point, and T max point we have identified as the 5 over here, right? So that we can do. Then we have few examples. We have gone through few examples. For an example, h is given 1 to 0 minus 3, x is equal to 1, 1, 1. We will find the T minimum value over here. L we can find out over here with the same way, right? T maximum we can find out by this T minimum plus L minus 2 way. And then by using this tabular method, we can identify all these elements, right? But here we have find the T minimum point is minus 1. It means the first value of y is located at t is equal to minus 1, right? So what is the reference point? The next point is the reference point because it is located at t is equal to 0. So we saw by there. And what is the T maximum? So T maximum is T minimum plus L minus 2. So if you follow this formula, so T max can be obtained as a 4. So that 4 is the last value of this. We can say T4 is yes, this is the last value. This is located at t is equal to 4. So this first value is located at t is equal to minus 1, and the last value is located at t is equal to 4, and all other points are located meanwhile. So that is one more example which is given as a exercise for you, and 1 or 2 students have already answered it out correctly. So this is the way how we can find the discrete convolution, right? So discrete convolution is basically applied between the input signal x of t and h of t, and then finally we are able to find this y of t. So y of t, output y of t of any signal is the convolution operation between the signal x of t and h of t. Okay. Then in the next lecture, we have discussed about some useful property of the convolution operation, and came across the first property of convolution operation. The first property is related with the unit impulse signal. So it tells us if you have a one system and if you give the input of the system as a x of t signal, then the system response is considered as h of t. Then we have a output as a y of t. So y of t is obvious the convolution operation between the input apply x of t and h of t signal. But if this input x of t is the unit impulse signal, right? We assume here this x of t, given x of t signal is the unit impulse signal, then output y of t is nothing else but this is equivalent to h of t, that is system response. So very importantly, we need to note down over here, if we apply the convolution operation between x of t and h of t, then it produces a h of t only. X of t can be eliminated and that it produces h of t only. So y of t is obtained as a convolution operation between x of t and h of t, and then we have an output as h of t. But this is applicable. Only which is only when your input signal x of t is a unit impulse. For all other cases, this is not a valid. So this is valid only. This output is equal to the system response h of t. This one is valid only when the applied input signal is a unit impulse signal. Right. So this is very, very importantly we need to note it down. And this is very useful property because in some of the cases where you don't know about the system response, we are interested to know the system response. So in such kind of a cases, input signals, so we are giving the input signal as a unit impulse signals, and whatever the output is obtained at the another end of the systems, that is equivalent to the system response, and that can be recorded and can be stored, right, for a further process. So the system response for a systems which the system response is unknown, that can be known only when we apply the input of a system as a unit impulse signal. So that is very important property. So that will tell us this very useful things. If the applied input signal is the delta of t, means the unit impulse signal, then very importantly, then obtain output y of t represents the system response h of t. Very importantly, you need to note it down, right? System response h of t. And what is the application? So there is very and that is if we are transmitting some signal from transmitter, and at the receiver end we are receiving something. Let's assume the transmitter signal is x of t and the receiver signal is y of t. Now if we know the system response h of t, then our communication systems can use the equalizer to eliminate the effect of wireless channel, and we can retrieve our original signal back. So if we know the h of t, so that it is better that output can be recovered in a better form, or make we can establish a very nice very good reliable wireless communication systems in the case when h of t is known. But this wireless channel is continuously changing with the time, and that's why the response is unknown. So idea is that the x of t, we are transmitting x of t signal as a impulses, and this signal is known as a pilot signal. X of t is actually the composite version of multiple unit impulse signal. And if you are transmitting such kind of a signals, then whatever the y of t is obtained, it is equivalent to the system response. Means the wireless channel system response can be identified at the receiver side. This is very useful applications for a wireless communication engineering students. More detail regarding this that we will discuss in a later stage whenever we discuss about the digital communication system. But at this point, we need to understand that if our input signal is a unit impulse signal, then the obtained output y of t is the same as the system response h of t. Taken one example to prove this. We have taken one examples. We are not going into detail because we have already done this before your final semester examination. But just to take a look around this, we have considered h of t is 1, 2, 0, minus 3, right? Here it is given, but assume that is unknown at the receiver side or at the output of the signal. And x of t is a unit impulse signal. So we apply, we go with a graphical method, and if you find the value of y of t, so this y of t is obtained as a 1, 2, 0, minus 3, and surprisingly this value is the same as our channel h, 1, 2, 0, minus 3. Here we are getting 1, 2, 0, minus 3, and if we consider our input signal as a delta of t unit impulse signals, then whatever the y is obtained as a output of the convolution operation between the input signal x of t and the system response h of t is exactly similar to the system response h1203. So you can assume the point to point over here, all these points are equal, so we can say our output, this can be proved over here, the output can be equivalent to output response is equivalent to the system response, provided the input signal is a unit impulse signal. So this is the property number one. You can go with some more example. We have already gone through some more example, right? And this property has already been verified in a lecture. Okay, so this is very useful property. Property number one, if any signal is convoluted with the unit impulse signal, so that is equivalent to the same signal. Any of the signals is convoluted with unit impulse signal, so we are obtaining the same signal, right? Okay, so next property is the convolution property is known as a commutative property. Commutative property means if we apply the convolution in either order, then the resultant output would be the same. For an example, if we can say we have been provided the two signal x1 of t and the system response is x2 of t, or if there are two different signal x1 of t and x2 of t, and if we apply the convolution operation here, so what we can identify is the convolution operation between these two signal x1 of t and x2 of t, it can be obtained as a integration. It's actually addition, but if you talk about the continuous time signal, so those additions are converted as a integration, because in a discrete time we have a finite number of samples are there. In case of a continuous time signal, we have an infinite number of samples. Whatever addition is, this addition in a discrete time is actually converted to the integration in a continuous time signal. All other things remains the same. So here we can say this one is tau into x of t minus tau d tau, and if we this one the first and x1 secondly, so that is this integration limit us as the x2 tau into x1 t minus tau. But after it all, if we prove this one, we can say anyway, if we prove this, we can obtain the same answer. Either we go with the x1 of t first and x2 second, or we make the convolution where we take x2 t of t first and x1 of t second. The formula is changed. If we take the x1 of t as a first, then it is x1 of tau. If we take x2 of t second, then it is x2 t minus tau. But if we reverse the order, then x2 of t is first and x1 of t is second, then this integration is here x2 tau into x1 t minus tau. So this order is going to change. But finally, if we answer it out, if we solve this, then equation number 1 and equation number 2 look same, and they are giving the same resultant value of the signal, and then we can prove that x1 of t convoluted with x2 of t is equivalent to x of t convoluted with x. Properties known as commutative property of the system. This is very important property, and you can prove this one at later stage. Here, now we came to the in which we will see about the distributive property. The next property is the distributive property. Distributive property will tell us if we are making a convolution, x1 of t is convoluted with the x2 of t plus x3 of t. So if the signal is the addition of x2 of t plus x3 of t, then it is equivalent to taking the individual convolution of x1 of t with x2 of t and x1 of t with x3 of t in then addition. So that is equivalent to this, right? So what it indicate again? This x2 of t plus x3 of t, if it is convoluted with x1 of t, so it is equivalent to x1 of t is convoluted with x2 of t first plus x1 of t convoluted with x3 of t second, right? So that will gives the same. So this is known as a distributive property. Next property is associative property. So this associative property will tell us if we are making a group of x2 of t convoluted with x3 of t, and then if you multiply with x1 of t, sorry, so this again we convoluted with x1 of t, so it is equivalent to we convoluted. So here we convoluted first x2 of t. This is the first priority. The first we convoluted x2 of t and x3 of t, and secondly we convoluted with x1 of t. But here if we change this order, first we convoluted with this group. This group is first convoluted x1 of t and x2 of t, and then secondly we convoluted this answer, right, with x3 of t. So both will give the same answer. So this property is known as a associative property. So property will tell us if x2 of t convoluted first, then convoluted with x1 equivalent to x1 of t and x2 of t convoluted first with x3 of t. Okay, so next operation is the next property of convolution is the time delay property. So time delay property will tell us if your input signal, if our input signal is delayed by some amount, so how it is reflected at the output, right? If the input signal is delayed by some amount, so how it is reflected at the output. As an example, consider two signal x1 of t and x2 of t. So first signal is x1 of t and second signal is x2 of t. We apply the convolution operation between these two signals x1 of t and x2 of t, and as a result of this convolutions, we are able to generate the new signal that is x3 of t. So x3 of t is obtained as a convolution operation between the signal x1 of t and x2 of t. Now let's assume the first signal x1 of t is delayed by some amount. This amount is known as a tau amount. So after this delay, this x1 of t signals can be represented as a x1 of t minus tau. So this part represent this signal x1 of t is delayed by this amount tau amount. Then we are convoluting with the x2 of t. So x2 of t is not going to change; it remains same. Only the first signal is delayed by some amount tau. So if we have this, we are assuming this x1 of t convoluted with x2 of t is x3 of t, and then x1 of t is delayed by some amount tau. Then the output x3 of t is also delayed by the equal amount tau, right? So then we find the convolution between after delay of first signal x1 of t with some tau amount, that is x1 of t minus tau. If we convolute it with x2 of t, then it is obtained as a x3 t. So it means if the first signal is delayed by some amount tau, so output is also delayed by the same amount tau. Or equivalently, rather than the first signal, if we assume the second signal x2 of t is delayed by some amount tau, so again we can obtain the same result if any of the signal, first signal, maybe either first signal or second signal will be like amount tau. So, but maybe is also exists here, in which we assume the first signal is known as tau 1. The second signal is also delayed by output. Then what happens about the output? So if the first signal is delayed by some amount tau 1, the second signal is 2 of t, which is also delayed by some amount tau 2, then the final outcome x3 is delayed by the addition of this by the addition of the first signal delay tau 1 and the second signal delay tau 2. So it is the delay, third signal is delay with the amount of the first signal delay plus the amount of the second signal is delay. So it means it is the addition of, it is delay with the addition of tau 1 plus tau 2. Right? So this is a one example, and you can have some more practical exposure of this by taking one example. So you can do this. At some later stage, we will prove this whole property. Right? It means I take one small examples for your better understanding. We will take some example of this better understanding. Let's say you have the signal x of t, right? Is some signal as a rectangular function t, right? And if it is delayed by some amount tau 1 x1 of t, and if x2 of t is rectangular signal, it's with some amount it's a rectangular signal with some time t, and this is again a rectangular signal of t, right? So if you can say if the first and this x1 of t convoluted with x2 of t, we have x3 of t. This is suppose the triangular function of t. Right? So if we can delay this first with tau minus, and the second is also delayed by some amount, it means this is the rectangular function is delayed by now one amount. The next rectangular function, which is also delayed by some amount tau 2, then this triangular function, which is the resultant signal of the convolution between x1 of t and x2 of t, is also delayed by the amount t minus tau 1 minus tau 2, means the addition of the delay of the first signal and second signal. That is the important property. Then we can have some more example have been solved for this one, and one example is taken over here. For an example, if x of t is convoluted with the delta of t, and then here the output is y of t, but if any signal is convoluted with the impulse signal, so we have already proved that is equivalent to the same signal. So if h of t is convoluted with x of t, is the impulse signal, so we are getting h of t. The same way, if x of t is some another signal and it is convoluted with the impulse signal delta of t, so at the output after the convolution we are getting the same value of x of t. So in that case, let's assume if x of t is delayed by some amount with delta and convoluted with the delta of t, then we have output is also delayed by the equal amount of tau 1. If x of t is not delayed, but the impulse signal delta is delayed by some tau 2 amount, then our output signal x of t is delayed by tau 2, and assume the first signal x is delayed by some amount tau 1 and the impulse signal unit impulse signal is delayed by some amount tau 2, then the resultant signal x of t is delayed by the addition of the means the total addition of the first signal delay plus the second signal delay. So total delay of the output signal is x of t minus tau 1 minus tau. Okay. So this is very important, and we came to the last property of the and that is the Fourier transform and convolution. So Fourier transform is the process to convert any time domain signal into the frequency signal, because most of lies in a frequency domain. So for analysis point of view, every communication engineer should be very well about its spectrum property of the signal, because if most of the times they have to apply, they have to check how much bandwidth is occupied by the signals, what are the major components lies within the bandwidth of the signal. So for that one, to make such kind of analysis, the essential part is the or Fourier domain version, frequency domain version of the signals will be available. So if the signal x1 of t is in time domain, its frequency domain version is x1 of f, and if any signal is x2 of t, its frequency domain version is known as x2 of f. Right? So this is assume that is a pair x1 of t in time domain, x1 of f in frequency domain, x2 of t in a time domain, x2 of f in a frequency domain, and the way to convert the time domain to or the uh, mathematical foundation to convert any time domain signal into the frequency domain signal, that is known as a Fourier transform. So with the Fourier transform, any time domain signal is to be converted into the frequency domain signal if x1 of t is time domain. Then after taking Fourier transform, we can obtain its frequency x1 of f. If x2 of t is a time domain signal, so after taking the Fourier transform, we can have a frequency domain like that. So the convolution formula will tell us, this property will tell us, if we are applying the convolution at time domain between the two signals as x1 of t and x2 of t. So, and if we take the transform, so in another domain, I mean the frequency domain. So this is the in frequency domain, and this is the time domain. So if we apply the convolution operation in a time domain, so in frequency domain, it is the multiplication between the two components x1 of f and x2 of f. Right. So in time domain, we have applied the convolution between the time domain signal x1 of t and x2 of t, and it is a multiplication of the Fourier transform of x t and the Fourier transform of x. Consecutively, the multiplication between the x of f and x2 of f. This is very, very interesting property, and we will expose this property in fully detail to get the idea how this properties can be applied. So we summarize the things of today's lecture before we conclude the session. So today we have discussed the properties of the convolution. We have started with the property of a impulse signals. If any signal is converted with the unit impulse signals, then we are obtaining the same signal back. This is the first property. Second property is commutative property, where we have learned there is no any sequence to be maintained between the two signals. Convolution operation between two signals. So if x1 of t convoluted with x2 of t is equivalent to the x1 x2 of t convoluted with x1 of t. Then we have discussed about the measure properties, the distributive property, associative property, and then finally we came to the time delay property, where we have seen if any signal is delayed by some time amount, then the output is also equally delay. Both the signals of convolutions are delayed by some amount, and the output is the delay with the addition of the first signal delay and the second signal delay. And then finally we have uh, gone through the last property is known as a convolution property that tell us if the convolution operation is applied in a time domain, so it is equivalent to multiplication of its Fourier transform in a frequency domain. So this part we have done. Few more examples that we have already solved that we will take a look for a next lecture. So from tomorrow's lecture, that we will go through this example, few examples of convolution in more deeply before we are going to start the new session. Okay, so I think we need to move over here, but you just wait. So I am able to take your places, and after taking your places, you can leave the meeting. Have a nice day. Bye. And we'll just wait for a places. I will give you the signal, and I will take the places. Then you can leave the meeting. Okay, so just wait for 1 more minute. So I will take your presence. Okay, so I'm down your attendance. So now the meeting. Have a nice day. Goodbye. Is it audible?
Yes, sir.
Yes, sir.